All right, this video is section 5.1 of Al Grosch's book, Developmental Math 2. We're going to start with some factoring. The first section is factoring using GCF and grouping. So the first question right up is, what is factoring? Most of the time we're familiar with the word factor. A factor is a number that's used to multiply in order to get a product. We're going to start with prime factoring before we do any kind of algebraic factoring. Find the prime factors of 6. Most of the time people learn to do this by using a tree, but there's also the ladder method. So using the tree, I'm going to use the tree here because this is what most people are familiar with. We put some branches on, and down here we're going to write two numbers that will multiply to make 6. We could use 6 and 1, but that's not really going to help us because we still end up with a 6 down there. So we're going to use 2 and 3. 2 times 3 makes 6. It turns out that these are the prime factors of 6 because both of these numbers are prime numbers. So 6 equals 2 times 3. We're going to do the same thing on 27. Two numbers that multiply to make 27 are 3 and 9. And now when I look at these numbers, 3 is a prime number because it can't really be broken down anymore. The only numbers that make 3 are 1 times 3. So 3 is a prime number. We're going to circle that. However, 9 is not. There are other prime numbers that make 9. So we'll put 2 more branches here. 9 can be broken down to be 3 times 3. And there we have the prime factors of 27. So we're going to say 27 equals 3 times 3 times 3, or you could use exponents and write this as 3 cubed. The prime factors of 250. Now there are lots of different factors that you could write here that will multiply to make the 250, and it doesn't matter which ones you use. I'm going to use the two that are most obvious to me, 25 times 10. You could have used 50 times 5. You'll get the same prime numbers at the bottom. Now when I look at 25 and 10, neither one of these are prime numbers. They can be broken down a little more. So breaking down the 25, I get 5 times 5, and these are prime numbers. And breaking down the 10, I get 2 times 5. Again, these are prime numbers. So there's my prime factors of 250. So I'm going to write 250 as 2 times 5 times 5 times 5, which is coming from here. I just rearranged them in numerical order, 2 and then the 3 5s. And again, you could write this with exponents if you wanted. You could write 2 times 5 cubed. You don't have to, but you can if you want. All right, when we get down to number 4, we've got some variables in here now, which are actually, I think, a little easier to break down than numbers. However, we're still going to break down the 25. 25 is 5 times 5. So those are the beginning of our prime factors. Now, to break down x squared, we just tear apart the multiplication. X squared is 2 x's multiplied together. And to break down the y5, we're just going to have 5 y's multiplied together. And these are the prime factors of 25x squared y5. To break this one down, 100ab cubed. First break down the 100, which is 10 times 10, and the 10s break down to be 2 times 5. So I'm just going to write these in numerical order. 2 times 2 times 5 times 5, coming from here. And then I'm going to break down the variables and write them over here. So we have 1a and 3b. And these are the prime factors. Okay, we're going to break down 45 first. 45 is 5 times 9. The 5 is prime, so we'll leave it. The 9 is 3 times 3, and those are both prime. So we have 3 times 3 times 5. And then the variables. We have x to the 4th, which is 1, 2, 3, 4 x's, y squared, and a z, just one z. So these are the prime factors here. we have to know how to do prime factors before we can do GCF. So we're going to use this on the next page. All right, on this page, we're going to find the GCF of 36 and 90. GCF stands for, in case you don't know, greatest common factor. So remember, a factor is something that we multiply to get a product. So the greatest common factor is the largest number that will multiply to make 36 or 90. It's a number that can actually divide into. So even though it says greatest, it's a number that's smaller because factors are smaller than their products, and these are the products. So the greatest common factor is the largest number that will divide evenly into 36 and 90. We a lot of times use the greatest common factor when we're finding common denominators. So you might be familiar with the process here. Down here, the first step to find the greatest common factor of 36 and 90 is to use the tree. And here in your book, and I don't know if it's because of the printing or what, the branches for the tree are not here. So these are the branches here, giving you these prime factors here. So these are the prime factors of 36 down here, 2 times 2 times 3 times 3. And these are the prime factors of 90 over here. So you can use the tree and its branches to find those prime factors if you need to. And then we're going to go through a process here to figure out the greatest common factor. So common means something that they share, that they both have. What's in common here? So we're looking at both of these lists for 36 and 90 to see what do we see that is common to both of these lists. All right, there's some 2's and some 3's here, and there's also 2's and 3's here. There are 2 2's here, but only 1 2 here. So they only have 1 2 in common because we only see 1 2 over here. So the common factors here are 2. There's 1 2 common, so we have that listed there. This list has 2 3's, and this list also has 2 3's. So 2 3's are common, and you can see that listed here. So the common factors are a 2 and 2 3's, and when you multiply those common factors together, you get the GCF of 18. You can see that here. So it's a matter of inspection after you do the prime factors. What do they have in common? They both have 1 2. At least 1 2. They both have at least 2 3's. All right, so we're going to practice down here on 24 and 70. So the first step is, let's use the tree to find the prime factors of 24. Well, I know 24 is 6 times 4. The 6 breaks down to be 2 times 3, and the 4 breaks down to be 2 times 2. So the prime factors of 24 are 2 times 2 times 2 times 3, coming from right here. And then we'll do the same thing with 70. 70 is 7 times 10. Turns out 7 is prime. It doesn't break down any further, but 10 does. 10 is 2 times 5. So the prime factors of 70 are 2 times 5 times 7. Okay, so now to find the GCF, we're going to look in both of these lists to see what they have in common. So the GCF. What do we see in both lists? Well, this list has 3 2's, but this list only has 1 2. So they only share 1 2. They only have 1 2 in common. So that's part of the GCF. Do they have anything else in common? This list has a 3, but this list has no 3. This list has a 5 and 7, but so the only thing that they're sharing is the 2. So the GCF is 2. We're going to try it again on these 3 numbers down here, 45, 60, and 75. Using the tree, 45 is 5 times 9. 9 is 3 times 3. So we're going to write the factors over here. 45 is 3 times 3 times 9. Those are the prime factors of 45. 60 is 6 times 10. When we break down the 6, we have 2 times 3. The 10 is 2 times 5. So the prime factors of 60, 2 times 2 times 3 times 5. All those factors right there. We had another number over here to the side. Oh yeah, the 75. So 75 is 3 times 25. 25 breaks down to be 5 times 5. So there's our prime numbers right there. 3 times 5 times 5. So we'll write it over here. 75 is 3 times 5 times 5. And now to find the GCF, we're going to look through all three of these lists and see what they have in common. All right, this list has 2's, but the other two lists don't, so the 2 is not common. I have some 3's here, I have a 3 here, and I have a 3 here. Okay, so there's 3's common, but since these two lists only have 1 3, there's only 1 3 common. They all have at least 1 3. So 1 3 is common. And it looks like, is that a 5 right there? This is a 5, isn't it? It looks like the 5 is also common. They all have a 5. So we're going to put a 5 there as a GCF. And when we multiply those factors together, we get a GCF of 15. 15 is actually the greatest number, the greatest common factor, the largest number that will divide evenly into 45, 60, and 75. So that's what a greatest common factor is. All right, on this page we're going to practice greatest common factor with algebraic expressions. So we have first 9x cubed y squared and 15x y to the fourth. We're going to find the greatest common factor of these two algebraic expressions. And you can see here that they've been broken down into prime factors. 9 is 3 times 3, and then we have the 3x's and the 2y's. 15 is 3 times 5, and then we have the 1x and the 4y's. And now we're going to look to see what's common. So the greatest common factor of these two terms. All right, what's in both lists? They both have at least 1 3. So 1 3 is common. And if you know your multiplication facts, you know 3 is the largest number that goes into 9 and 15. So 3 is part of the greatest common factor. When we look at the variables, this one has 3 x's, this one has only 1. So they both have at least 1 x. So 1 x is common. And looking at the y's, this one has 2, this one has 4. So both lists have at least 2 y's. And so when we multiply all that together, we get 3x y squared as the GCF of those two algebraic terms. Okay, we're going to do the same thing down here. We have two new terms. We have 20x to the 5th y to the 6th and 150x to the 7 y cubed. So the first thing we're going to do is break it down into prime factors. And I'm going to write over here 20x to the 5th y to the 6th. Well, when we break down the 20, we have 2 times 2 times 5. And you guys can use the tree on that to figure those out. X to the 5th, 1, 2, 3, 4, 5. Y to the 6th. Okay. So 150. X to the 7, y cubed. 150. Well, if we need to, maybe we need to do a tree over here. Okay, 150 is 15 times 10. 15 is 3 times 5. 10 is 2 times 5. So those are the prime factors of 150. 2 times 3 times 5 times 5. So I'm going to write them over here. 2 times 3 times 5 times 5. And then we have 7 x's and 3 y's. After you get good at this, you don't really have to write all this out. I'm just writing it out to show you guys, to introduce to you what exactly a GCF is. And once you practice it a little bit, you won't have to write all this stuff out. So what do these two lists have in common? As far as coefficients here, they both have at least 1 2. So a 2 is common. It looks like they both have at least 1 5. So a 5 is common. Now with the x's, this list has 5 x's and this list has 7 x's. So they both have at least 5 x's. And with the y's, there are 6 y's in the first list and 3 y's in the second list, so they both have at least 3 y's. When I multiply all that together, I get 10 x to the 5th y cubed. You might know a shortcut for this. The 10 is the smallest number that goes into 20 and 150. X to the 5th, when you look at the x's, the GCF always has the smaller of the exponents. So this one's an x to the 7, this one's an x to the 5th. They both have at least 5 x's. This is y to the 6th, this is y cubed. The smaller one is a cube, so the GCF has the smaller one, and that's just a shortcut for you. Now we're going to find the GCF of 42 a cubed b squared, 63 ab to the 5th, and 21 a5 b to the 4. So let's write out. I'm only going to write the prime factors of the coefficients this time, because I think we can do the variables without writing them all out. The prime factors of 42 are 2 times 3 times 7, 6 times 7. The prime factors of 63, 3 times 3 times 7, 9 times 7. And the prime factors of 21, 3 times 7. So the GCF, what do we see in common? We see all three lists have at least one 3, and all three lists have at least one 7. So the GCF of the coefficients is 3 times 7, or 21. Now when we look at the variables, I'm going to try to, there we go. We have a cubed, a to the 1, and a to the 5th. So what's common? A and the smallest exponent is 1, so a to the 1. B squared, b to the 5th, b to the 4th. They all have b, and the smallest exponent is squared. So the GCF is 21 ab squared. All right, we're going to do a little bit of background here. We're going to go back to distributive property and simplifying just to review, so that when we get ready to factor, we can understand what we're doing. To simplify an expression like this, inside the parentheses here, these are not like terms. So to simplify, we would distribute the 3x to both of these terms. So that's what we're going to do. 3x times 2x is 6x squared. 3x times 5 is 15x. Now, the directions tell us to work backwards to get the original problem back. When we're doing this, we call it factoring out the GCF. We're going to start with the expression 6x squared plus 15x that we got from back here, and we're going to factor out the GCF. So we look at these two terms, and we find the greatest common factor. And we're going to write the greatest common factor here. Okay, so what's common? What's the largest number that goes into 6 and 15? Well, that would be 3. 3 is the largest number that will divide into both of those. Then we look at the variables. We have an x squared and an x to the 1. We take the x, and its smallest exponent would be the 1. So 3x is the GCF. Then we use some parentheses. Inside the parentheses, we're going to put two terms that will multiply times the 3x to give us these terms. So what times 3x gives us 6x squared? Well, 3 times 2 would give us 6, and x times x would give us the x squared. So 3x times 2x gives us back the 6x squared. And then what times 3x would give us back the 15x? Well, 3 times 5 is 15, and we don't need any more x's, because this x times no more x's will give us this x. So when you factor out the GCF, you end up with your original expression back. So factoring out the GCF is really just undoing distributive property. You put the GCF on the outside, and then whatever terms it would give you when you multiply to give you back the original expression. So we have another example down here at the bottom that says factor. I don't know if we have enough room to actually factor this here. But the directions will show you that when you factor these three terms, to factor out the GCF, you look for what's the GCF of 25, 15, and 5. The largest number that will go into all three of those is 5. You can see that down here. X cubed, x to the 5th, x squared. So we take the smallest exponent, and that would be x squared. Y cubed, y to the 6th, y to the 7. The smallest exponent is y cubed. So they've identified, the authors identified for you down here, the GCF is 5x squared y cubed. Now to factor it out of this expression, you're going to have to write it down and then divide it. And that tells you what will be left inside the parentheses. And you can check it by multiplying. When you multiply back, you get the original expression. This example is a little confusing. I think we're going to do some step-by-step on the next page. Okay, here we go. We're going to do it for ourselves here. So we're going to factor. We call this factoring out the GCF. We first look at our two terms, and we have to identify first on the outside what is the GCF. So the smallest number that goes into 10 and 15 is 5. It's the smallest number that will divide evenly into them. When we look at the a's, we choose the one with the smallest exponent. So we're going to have a squared. And we look at the b's, we choose the one with the smallest exponent. So we're going to have b squared. So that's the GCF. Now, we're going to undo the distributive property. I actually think I'm going to write this a little further down. So the GCF is 5a squared b squared. To figure out what's left in these parentheses, we divide each of these terms by the GCF. So we're going to divide by 5a squared b squared. Okay, and we've done this division before. We did it in chapter 4. So 10 divided by 5 makes 2. A squared divided by a squared cancels because they're the same. B squared, b to the 4 divided by b squared, remember to subtract the exponents, gives you b squared. And you can check mentally by multiplying these two terms. You should get this term. So if you check that, 5 times 2 is 10. A squared, there are no more a's here, will give you a squared. B squared gives you b4. So now we're going to do the same thing for the second term. 15 divided by 5 is 3. A cubed divided by a squared, subtract those exponents, gives you an a, just one a left over. And, oh, I'm sorry, that's not right. The b's don't cancel, do they? No, because you have a b squared, and should this be b squared? Yes, this should be b squared. I'm so sorry, they do cancel. So we're left with just 3a for this second term. And you can again check this by multiplying. When you multiply these two terms together, it should give you this one back. So 5 times 3 is 15. A squared times a is a cubed. B squared, no extra b's, b squared. So that's how you factor out the GCF. Let's do it on this one. What's the largest number that goes into 3, 9, and 21? That would be 3. Look at the x's. X to the 5th, x to the 7th, x squared. Choose the smallest exponent, would be x squared. Y10, y to the 4th, y to the 12th. Choose the smallest exponent, and this is the GCF. And now we're going to divide each of those terms by the GCF. 3 x squared, y to the 4th. And that will tell you what will be left in your parentheses. Okay. 3 divided by 3 reduces to make 1. X to the 5th divided by x squared makes x cubed. Y to the 10th divided by y to the 4th makes y to the 6th. Negative 9 divided by 3 is 3. X to the 7 divided by x squared makes x to the 5th. And the y's cancel because they're the same. 21 divided by 3 is 7. The x's cancel. And the y's, y12 divided by y4 makes y8. And of course you can check by using distributive property. Okay? When you multiply these terms back, you should get your original expression. All right. On this example, we have 65, 20, and 30. What's the highest number that goes into 65, 20, and 30? I believe that's 5. We have some y's common. If we choose the smallest exponent, that would be y to the 9. We have some v's common. If we choose the smallest exponent, that would be v to the 4. So this is the GCF. And we're going to divide all three of these terms by 5, y to the 9, v to the 4. All right. 65 divided by 5 is 13. The y's cancel because they're both the same. We get v to the 14 by subtracting the exponents. Plus 20 divided by 5 is 4. Subtract the exponents on the y's. We get y to the 21. Subtract the exponents on the v's. We get v to the 16. Plus 30 divided by 5 is 6. Subtract the exponents on the y's. And the v's cancel because they're both the same. And again, check by using distributive property. Check by distributing. If you multiply this times all three terms, you should get this original expression back. Okay, on this page we're going to do factoring using grouping, and really this is just an extension of GCF. We use this on expressions when they have 4 terms. All right. We're going to start off with something simple here, but it's a kind of a strange concept. When you look at this expression, there are really only 2 terms. This minus sign separates all of this is one term and all of this is another term. In this first term, we have 3 being multiplied times x plus 2. So these are both factors. We have negative x being multiplied times x plus 2. Both of these terms have an x plus 2 as a factor. Okay, so they are sharing, or they have in common, x plus 2. So it's possible for the GCF, or the common factor, to actually be a binomial. If you remember what a binomial is, it has 2 terms. And that's the case here. X plus 2 is a binomial. We see it being multiplied in both of these terms, so it is common. So if we bring it to the front like we did the GCF before, we are just factoring it out of both of those terms. And it looks weird to put it underneath in a fraction like we did before on the previous page, but when you do that, it cancels out of both those terms. And what you have left is the 3 that was up there at the front and the negative x that was back here. Now, if you wanted to check this, you could distribute this by using double distributive or FOIL. It would not come out to look exactly like this, but if you simplified this original expression, if you simplified it, it would be the same expression as if you did double distribute on this. So we're going to try factoring this expression here, 2ys minus 2yf plus bs plus bf. We use factoring by grouping when we have 4 terms like this that have nothing in common across all 4 terms. You can see the front 2 have some common factors and the back 2 have a common factor, but there are no factors that you see in all 4 terms. And this is when we can use factoring by grouping. To do that, we're going to separate this, and we're going to do GCF on the front and the back separately. This example, I don't like the way these examples are printed. In the front 2 terms, you can see there's a 2 and there's a y common, and when you factor out 2 and y, you're left with an s minus an f, and that turns into this. When you factor the back 2 terms, they have a b in common. When you undo distributive property, you'll end up with s minus f. And now these 2, the front and the back, have s minus f in common, so you can bring that to the front, and you end up with 2y plus b. This looks confusing, so we're going to practice it down below here so that you guys can see what really happens when we do the whole thing. All right, again, we only use this when we have 4 terms, so I'm going to use a vertical line there to separate my terms. And just working up here in the front, I'm going to do GCF. What do they have in common? Well, both these terms have a y, and that's the only thing they have in common. But when I factor out the y from both those terms, I'm left with x plus 3. Usually this sign right here comes straight down in between your two terms. These two terms have a 6 in common. They're both divisible by 6. But because I put that minus sign there, I'm actually factoring out a negative 6. So I'll write negative 6 under each of those terms to figure out what's in the parentheses. So the negative 6's cancel, and I end up with an x. But now I have a negative divided by a negative makes a positive, and 18 divided by 6 is 3. And you can see now both of these have an x plus 3. So now I have a common binomial. These both have x plus 3, so I bring x plus 3 to the front. I'm actually taking it out of both of these terms by doing that. I'm factoring it out, and I have left y minus 6. After you do this a few times, it's not nearly as complicated as it looks. It just takes a little bit of practice. So we're going to practice this, I think, on the next page. All right, we're going to factor 10k plus 10m minus km plus m squared. All right, so as I'm looking through my book, I'm noticing that my example here has different signs from the most current book. So I'm going to scratch this example here and rewrite it. I think this will be more like what's actually in the most current book. So 10k minus 10m minus km plus m squared. The signs are just different. So we're still going to do factoring by grouping. So we'll cut this in half. So what do these two terms have in common? They're both divisible by 10. They don't have any variables in common. When we factor out the 10, or we divide both these terms by 10, we're left with k minus m. The negative sign will come down. What do both of these terms have in common? Well, they both have a factor of m. But by putting this negative sign here, I'm now dividing by negative m. So I'm going to divide them both by negative m. It helps if I actually write what I'm saying. Okay, negative m. So when I divide this, I'm just left with k. When I divide positive divided by negative, I get negative m, because this is a square and this is a 1. And you can see I now have k minus m in common, which I can bring to the front. So I'm taking it out of both of these terms. I'm factoring it out, and I have left 10 minus m. And if you check by distributing, you will see that you get these same exact terms back by distributing this. Well, it'll be these terms because I changed the question. All right, let's try this one. I have 4 terms, so I'm going to cut them in half. What do I have in common here in the front? They both have a factor of x. When I divide by x, I have x minus a left. Bring down this minus sign. Now, these two terms have nothing in common. This is an x factor and this is an a factor. They have nothing in common. So when this happens, we're just factoring out a 1. 1 is always in common with everything. But because I put this minus sign here, I'm actually factoring out a negative 1. So divide both of these terms by negative 1 to figure out what will be in the parentheses. Negative x divided by negative 1 makes positive x. A divided by negative 1 makes negative a. And the key to factoring by grouping is that these two binomials here have to always match. You can't go to the last step if they aren't the same because they are now common. And you're factoring them out or taking them out of both of those terms. And you have left x minus 1. All right, down here at the bottom, when you initially look at this, you might want to separate this in half and factor out a 5 here and a 25 here. But with factoring, now that we've learned two different kinds of factoring, the first step is always to look for a GCF across all terms. Is there anything that will divide into all four of these terms at the same time? And of course, they're all divisible by 5. So we're going to factor out a 5 as a big GCF first. So we're just going to divide all these terms by 5. And this is factoring out a GCF as the first step always. So when we divide by 5, we have bx plus bz plus 5x plus 5z. Just by dividing by 5, and that's a GCF. Now that 5 GCF is not really going to do anything else, but it will be in our final answer. Now these four terms in this parentheses here, we are going to separate in half and factor by grouping. So these two terms both have a b. They have a common b. And when you divide by b, you'll end up with x plus z. These two terms have a 5 in common. So we have the plus sign coming from there. When you divide them both by 5, you're left with x plus z. And again, making sure these two binomials match because they are the common binomial, and now we'll bring them to the front as x plus z. Taking it out of both of these terms, we're left with b plus 5. And that's the final factoring right there.